Welcome back, everyone. In this video, I'll begin going over the lecture for the volumes by cylindrical shells section. So cylindrical shells will be just a different method for finding the volume of a revolution of some region. And the main reason we're going to need it is there are certain situations where you can figure out the volume of a region when it's revolved around some line. However, we might not be able to actually set it up in the washer or disk method way. And that's where this method of cylindrical shells is going to come in. So this is kind of the iconic example to explain why you need cylindrical shells. Now since it is iconic, you'll probably look it up and find this exact example elsewhere. But any curve that does not pass the horizontal line test, you can't actually figure out the volume of revolution using the disk or washer method, at least very easily, when it's revolved around a vertical axis like the y-axis. So here's really the setup. You have this region. It's bounded by the x-axis, y equals 0, and the curve y equals 2x squared minus x cubed. But once again, this can be any graph that when you make it, it's not a one-to-one, which means it doesn't pass the horizontal line test. So something like the graph of sine of x would also be an example that you could do here. But the main idea is that if you want to rotate this around the y-axis, there's a couple things working against us. One thing is that if we rotate around the y-axis, we know our slice is going to be this horizontal shape that's going to be brought around and revolved around the y-axis here, kind of thick. And the only problem with that is we would need the washer method here, but the inner radius and the outer radius are part of the same curve. They're part of the same formula. But also a bigger problem is that because you're rotating around a vertical axis, go back to your notes and look at the last section, you need the formulas as x equals. So we would have to solve this equation. We would have to solve this equation for x. And this is extremely difficult to do. It's possible, but it would take an extremely long time. A lot of techniques would go into it. And then after that, you would figure out, okay, which one, because you'll get multiple equations for x, which one is the inner one, which one is the outer one. Then we have to set up that entire integral with the washer method. So this is where cylindrical shells comes in, because this is a relatively simple formula. It's not complicated. It's just a polynomial. We should be able to do it. Well, what's going to happen here is if you view this region being rotated instead of in horizontal slabs, but in vertical slabs like this. So the original one I have drawn here, this slab is right here. And you rotate the vertical slab around the y-axis. What you get is you get what it looks like a cylinder, the surface of a cylinder with some thickness. So it's not actually just a cylinder, because the idea is we would take these vertical slabs, they have some thickness, because we know with the rectangles, it's not just, a single line. We've done all these approximations with rectangles, but it looks like the surface of the cylinder with some thickness. And now you could call the thickness, like here, you could call it delta X or something, whatever it happens to be. It's not a big deal. But the idea is looks just like the surface of a cylinder with some thickness. So what is the volume of this cylinder looking thing? Well, the surface area of a cylinder is equal to, and there's two components here. You have the height of the cylinder. Go ahead and find a color here. So we have the height of the cylinder, which is h. And then you also have the radius of the cylinder, which I'll use lowercase r. The surface area of a cylinder, got the word area, is 2 pi RH. Well, if we were talking about just the surface area, then this would be our formula for the this, and we would add them all together, do our Riemann sum thing. But we can't forget that there's actually some thickness to it, so you multiply it by that thickness delta x. All right, so this portion is the surface area specifically, but because it has thickness, it's actually a volume. And that's our delta x. This is like our b minus a over n as referring it to old stuff, but we're just going to use delta x for simplicity here because we know what's going to happen if we approximate the region by all these rectangles. Then we add all these surface areas up, we take the limit as n goes to infinity, and it becomes an integral. And exactly what's going to happen here, the formula for cylindrical shells once again, this is going to be, it's going to give you the same formula that if you were possibly able to use the washer method, you would get. The volume is, in this example specifically, it would be 0 to 2, but in general, a to b. I'll write down the setup. And we have the surface area here, pi, or actually 2 pi, don't forget that 2, because the other one just has pi, times r of x times h of x. And then the delta x is what becomes the dx. That's the b minus a over n. That's what becomes dx when you do the limit as n goes to infinity. We've seen that a few times. And most people like to go ahead and just factor out the 2 pi in their formula, sort of like we did with the pi eventually in the last section. So 2 pi from a to b of r of x times h of x dx. Now with similar to the last section, if you're doing cylindrical shells and you're rotating around a vertical axis, then you're going to have these vertical slabs. So everything's going to be in terms of x. If you rotate around a horizontal axis, but you're doing cylindrical shells, then everything will be in terms of y. So let's just go ahead and write that. If doing cylindrical shells about a horizontal axis of revolution, everything is in terms of y. But it's exactly the same formula. It's 2 pi. You figure out your bounds in y from a to b. It's just that your radius formula is r of y, and your height formula is h of y dy at the end. But the entire point here is that they're exactly the same formula, just like last time. So when we see one formula and work it, we can take that and transfer the same ideas to our other picture. You really just need to keep track of what is the radius formula, what is the height formula. And going back here, you kind of look at this cylindrical shell that I've drawn the sample of. The radius is x because it starts at 0 and it goes all the way to whatever this x value is. Now that depends on the picture. And then the height also depends on the picture. This time the height is actually the function value because it starts at 0 and goes up to the y equals curve. So y equals 2x squared minus x cubed curve. So in general, r of x, h of x, you just have to look out for like we did with the previous section. And that's why drawing a picture helps so much. But r of x, the way I like to think about it, r of x is the distance. The slab, whatever we are rotating around, is away from the axis of rotation. And h of x, when you look at your slab, it's just the height of that slab. Now, if you look up formulas, it'll actually give you very specific formulas. So if you're in this exact scenario where you're rotating around the y-axis very specifically, then your radius is just x because you're looking at from x equals 0, which is the y-axis, to where your x value is. That distance is 0 to x, which is x. The height, if your region here is just bounded by the x-axis and then your curve is all above it, then your height is exactly the function value f of x right here. But if it was like y equals -1, then we would have this -1. It would be top minus bottom. And it also depends, are you doing cylindrical shells around a vertical axis? So are the cylinders vertical like this? If you rotate around a horizontal axis, then you can imagine that the cylinders will be horizontal. And so you just have to take this idea of what they're representing. This is why drawing a picture is so important. All right, so with that, we'll go ahead and actually do our perfect setup problem here. It says find the volume of the solid obtained by rotating the region bounded by y equals 2x squared minus x cubed and y equals 0 about the y-axis. So this is the same exact thing as before, which means, yes, I'll draw the region because that's a good idea and the axis we're rotating around, but I'm not going to do anything extra because we really talked about this setup. We've got the y equals 2x squared minus x cubed. It looks something like this. We saw that the bounds were from 0 to 2. And then we also wanted to be bounded by the x-axis, which is y equals 0. So this is our r. Same exact thing as before. And we want to revolve or rotate, whichever one you like to use, around the y-axis. So this is our axis of rotation. All right, so in general, how do I visualize this? How am I going to know what my r of x is, my radius formula is, what is my height formula? Well, I'm going to go ahead and just draw a vertical slab. It can be anywhere. Keep in mind that when you kind of draw it, it's a left or right rectangle approximation, so you shouldn't draw it angled. It should just be flat, but it's not a big deal whether it's a left or right when you draw it. And the main thing is that if you go out here, this is your r of x. So just think back when we rotate this around. This is why I wanted to do the first one. When you rotate around your axis, the distance between them is your radius. So this is our formula r of x. Well, if this is our x value chosen here, then r of x equals, what is this distance? It's x minus 0, which is just x. Now, if that's not comfortable yet, just imagine if we chose a different slab here. So let's say this one, and we rotate this one around, then our radius is this. But what is the radius here? This would just be a different x value I chose to use. So it's r of x no matter what, because it's x minus 0. And, you know, the thing to think about, what if we were rotating around x equals -1? Well, then it would be, what's the difference from -1 to x? It would be x minus -1, which is x plus 1. So that's how it's going to change, if it does change. Now, what is the height of our slab here? H of x. Go ahead and use different color. Well, the height here is just since it's a vertical slab, is the top minus the bottom. Because once again, when we rotate it, this is going to be the height of the cylinder. At this portion, when we rotate it, this becomes the height of the cylinder. And we just do top minus bottom. The top is the function, which is 2x squared minus x cubed. And the bottom is the other function, but it's the x-axis, which is y equals 0. I'll put parentheses around each to clarify this is the top and this is the bottom. But when we simplify, it's just the 2x squared minus x cubed. All right, and then the volume by cylindrical shells. So I'll just write that we're using cylindrical shells here, but this was our setup problem before. So we know that we get 2 pi. The integral, well, from a to b, we won't plug that in yet. But inside we just have r of x, which is x, times h of x, which is 2x squared minus x cubed dx. Now, what are the bounds here? Well, the thing to notice is that you have x's everywhere, and we have a vertical slab. So the bounds are the x bounds of our picture, the domain of our region here, and it starts at 0 and goes up to x equals 2. Right, so we don't care about the y value. I didn't even specify what's the y value up here. I don't know. Not a big deal because we only care about x's. All right, so we have everything plugged in, and now at this point, just like with the previous section, really all the previous sections when we started these applications, once you have it set up, you just integrate this. But do we have to simplify a little first? We do. We don't have a multiplication rule, so we have to distribute the x. We get 2x cubed minus x to the fourth dx when we distribute. But now we can integrate this, and we can integrate this because we know how to integrate each part. The antiderivative, the 2 stays there. The integral of x cubed is x to the fourth over 4 minus the integral of x to the fourth is x to the fifth over 5. No substitution, so we just directly know we're going to plug in 0 and 2. Now, before I plug in, just going to knock this 2 off, simplify it with the 4 to make a 2 there. And we'll go ahead and finish this up. So we got 2 pi. Then we'll go ahead and plug in x equals 2. Subtract. Plug in x equals 0. Now you might already be able to see that when we plug in x equals 0, we will get 0 because it's just powers of x there. For x equals 2, we get 2 to the fourth over 2. That's not a 2 though. 2 to the fourth over 2 minus 2 to the fifth over 5. And just finish this up here. 2 to the fourth is 16. 16 over 2 is 8. Minus 2 to the fifth is 32 over 5. And 8 is 40 over 5. So 40 minus 32 is 8. And we get 2 pi. And on the inside, it's 8 pi over 5. Or just 8 over 5. We don't have a pi there. Pi's on the outside, and I already included that. So it's just 8 over 5 because this was 40 over 5. 40 minus 32 is 8. And then when we distribute that, we get 16 pi over 5. All right, so that's a good preview, but kind of think about that. We spent the first 10 to 12 minutes just talking about the setup for this one. So we knew we were going to use cylindrical shells. We knew exactly what the picture looked like. When we jump forward and do some more problems related to cylindrical shells, you'll have to go through, graph the picture, see what the region looks like, and then make a decision on how you're going to do it after that. So I'll see you there.